Welcome to the 20th part of Mechanical Properties of Fluids, and in this part you will learn about Ascent formula. Ascent formula. Consider a capillary tube of radius r dipped in a liquid of surface tension sigma and density rho. Suppose the liquid filled in the capillary tube wets the side of this tube. That means the meniscus will become concave and the shape of the meniscus of water will be nearly spherical if the capillary tube is of sufficiently narrow bore. Here is a diagram of rise of liquid in a capillary tube. At point B, you can see that the liquid rises in the capillary tube and forms a concave meniscus. Point B is below the meniscus in the liquid and point A is above the meniscus in air. PA, the atmospheric pressure, is the pressure at point A, and at point B the pressure therefore will be PA minus 2 sigma by R, because you know that the excess pressure is 2 sigma by R. Figure B shows the enlarged view. The angle of contact here, you can see that it is theta. So, the same angle will be formed between small r and capital R. Here, capital R is the radius of the curvature of the concave meniscus. And if theta is the angle of contact, then from the right angle triangle shown in the diagram in the previous slide, small r by capital R will be equals to cos theta, or capital R will be small r by cos theta, and therefore the pressure will be 2 sigma cos theta divided by small r. Means you have to put the value of capital R in P is equals to 2 sigma by R equation, and you will get 2 sigma cos theta by small r. Due to this excess pressure P, the liquid rises in the capillary tube to height h. When the hydrostatic pressure exerted by the liquid column becomes equal to the excess pressure P, that means at equilibrium P must be equals to h rho g. By putting the value of P means 2 sigma cos theta by R equals to h rho g, you got h is equals to 2 sigma cos theta divided by R rho g. And this is the Ascent formula for the rise of liquid in a capillary tube. If we take into account the volume of the liquid contained in the meniscus, then experimentally it is observed that the exact height h will be 2 sigma cos theta by R rho g minus R by 3. However, if the capillary tube is very narrower, then R by 3 factor is neglected, because as I have told you that the capillary tube is of hair-like thickness, but it is not possible practically. So we have to take a factor of minus R by 3. The Ascent formula shows that the height h up to which the liquid rises in the capillary tube is inversely proportional to the radius of the tube, directly proportional to density of the liquid and surface tension of the liquid. Hence, a liquid rises more and more in a narrower tube than in a wider tube. Now, here comes the case when what will happen to the liquid if the rise of liquid in a tube of insufficient height. As we have calculated already, shown in the first diagram of the following slide, that the height up to which the liquid rises in the capillary tube is 2 sigma cos theta divided by r rho g. Now we put the small r is equals to r cos theta again in the formula of H. Then you will get 2 sigma cos theta divided by r cos theta rho g. Means 2 sigma divided by r rho g. Now in this formula, sigma, rho and g all are constant. That means you can say that H is equals to constant divided by capital R. Or you can say H into capital R is constant. And if it is constant, then it must be constant for any other pair of H and R. Means H into capital R is equals to H dash R dash, where R dash is the radius of curvature of new meniscus at any height H dash. As H dash is less than H because it is of insufficient height, so R dash must be greater than R. Hence we concluded that in a capillary tube of insufficient height, the liquid rises to the top and spreads out to a new radius of curvature R dash. And the R dash is given by H divided by H dash into R. But the liquid will not overflow.